Today we want to talk about double integrals, and we want to start to figure out how to calculate a double integral. Most of the interesting stuff is going to happen in describing the region. So just recall, we're trying to find the volume under a surface and above a region R in the XY plane, and it's given by this double integral. We integrate over R, the expression f of xy times dA. dA is a little rectangle of space in the region R that we're going to use for an area. And then we're going to evaluate the function at some point in that little rectangle of space in R and use that for a height. Multiply the height times the area to get the volume, and then add up all those little rectangular solids everywhere we have a point XY in the region R. Our task is going to be describe the region in such a way that the integral will understand. We want to describe the region R so that the integral can understand what's going on. There's no trick to it. It's just a simple trick. Instead of like a simple integral where we say x is between a and b, we just say two things. What's x between? What's y between? That's how we're going to describe the region. What's x between? What's y between? True. I never said you should trust me. In fact, the amount of trust that you have for me should increase a little bit, because my stated purpose is to help you learn calculus. But given the nature of the relationship between teacher and student, that puts me in a position of authority over you, at least as far academically, which means that you should trust me less. It puts us back onto the footing of psychology. Probably shouldn't trust this dude. At the very least, I'm telling you not to trust me. Verify the stuff that I say. You know what I mean? That's what you like to think. All of a sudden, it's a Vizzini problem. So here's how we're going to describe the region for the integral. We're going to say what's x between and what's y between. This is the double part of the double integral. This will be the double part of the double integral. The tricky part is that x and y are not always going to be between constants. We're going to break our integral into a double integral, and we're going to separate dA into a dx and a dy. We'll have a dx and a dy. Like we mentioned yesterday, we'll have an x integral, and the dx is closest to the function, so the integral that's closest to the function will be the x integral. So we'll have a dx, and this first integral will be associated with the x. Here's where we're describing what's x between. And then our other integral can be a dy. And so this outer integral will answer the question, what's y between? We can also set this integral up in the order dy dx. And we just have to, if we switch the order here, we just have to make sure we switch the order here. So I can make my inside integral dy. And then I'll make my outside integral dx. The integrals that we're setting up here are referred to as iterated integrals because we can do them one piece at a time. I could do the dx part, finish that up, then do the dy part. So these are iterated integrals. This means we're going to be doing them in parts. The focus here is not going to be on finding the antiderivatives. The focus right now is going to be on describing the region, answering the question, what's x between and what's y between? Sometimes it's super easy, barely an inconvenience. The easiest thing that we could do is just set up a rectangle. We want to think about what's x between and what's y between. The function itself, not important. But we're going to set up two double integrals. One of them will be a dx dy integral. And the other one will be a dy dx integral. So in this case, we just have to look at what is x between. So if we pick at all these different y values, x starts off at 0 and ends at 9. Because we just have a rectangle is just the intersection of two intervals. That's why this one is most basic. X goes from 0 to 9. And while x goes from 0 to 9, y goes from 0 to 3. Rectangles are easiest to describe because it's just the intersection of two intervals. And these two intervals are interchangeable. So as long as the x's go with the x's and the y's go with the y's. So we could also describe this with the integral an integral dy dx, where y goes from 0 to 3, and x goes from 0 to 9. Rectangles are easy because it's just the intersection of those two intervals. It's just interval by interval. And the intervals are all. No, that's much more complicated because we would have to describe all the x's and all the y's and not have a one-dimensional thing. It'd be kind of a mess. If we just do it, if we do this double integral f of x y over some a one-dimensional region, then we're going to have zero volume. So weird stuff happens if you start taking everything out. So we're going to play with this rectangle, and we're going to start cutting this rectangle down into pieces. So let's suppose that we have this region. Now that we don't just have a rectangle, we are going to have to be more careful about what we say x is between and what y is between. X from 0 to 9 and y from 0 to 3 only describes this rectangle. But that's not our region. Our region is this bottom half of the rectangle. Question? Capital R is just for region. That's just the name of the region. So up at the top, we're integrating over some region R. So when we go from left to right, we can see that the lowest x value is 0 and the highest x value is 9. And we still have the same, we're still sitting inside the same rectangle we had in the previous problem, from 0 to 9 and from 0 to 3. But for all x values, we don't want all the y values from 0 to 3. At a given x value, we only want some of the y value. Similarly, for a given y value, we only want some of the x values. So for example, at this x value here, I only want some of the y values. And for this y here, I only want some of the x values. So that's what we have to keep in mind. So let's set up a double integral, and let me mention one of the other rules for setting up a double integral. When you're setting up a double integral, the last integral, the outside integral, only gets to use constants. That outside, or the last integral, only gets to use constants. Earlier integrals can use functions of upcoming variables. This is, I think, the language I'm going to settle on for this. It's changed in the past. So here's our last integral. We have to put constants there, but early integrals can use functions of upcoming variables. It's like reading a rule book when we don't have all the rules yet. So this will make more sense as we go. Like reading the rules and being like, oh, what do you mean bonus action? Because you haven't got to the part about action economy or anything like that. So let's set this up with a dx dy integral. So my x will be the first integral that we come across, and our y integral will be the last integral we come across. Now, this is just how we do things. Once we start making the calculations, it will make more sense. So I don't know if you want to make calculations first. Do it this way. I chose this way. So since the last integral can only involve constants, that's the one that we should start with. Because the only thing that we can say y is between is 0 and 3, because we have to use constants. I don't know where I picked up the habit of calling this the last integral and not the outside integral, but damn it, that's what I've been saddled with. I think it happened when I took Calc 3. My instructor called it the last integral, probably because his instructor called it the last integral. We should have all called it the outer integral. And when we get together, we're like, oh, son of a bitch, we should have called it the outer integral, because now we have to tell them shit like, do the last integral first. And students are like, oh, what? When you're setting it up, when you're setting it up. Do your outer integral first, because it has to be constant. Now, that's just based on the lowest y value and the highest y value we see. So it has to be constants. Now, for the x's, we have to decide for a given y value, what is x between? Because the question is still, what's x between? What's y between? So for all the y's between 0 and 3, what is x between? X starts off at the line and ends at 9. So we pick a typical y value. Where does x start in the region? Where does x end in the region? So x starts at the line up here. X starts at the line and ends at 9. I didn't realize it was going to line. So our first x value will be whatever the line is, and our second x value will be the 9. Let's put that in, because that's easy. So here we have a line with a slope of 1/3. So y is equal to 1/3 x. But that's the y version of things. This line has equation y equals 1/3 x. I don't want to know what y is as a function of x. I want x to be a function of y. So I just turn this equation around. X is equal to 3y. So start off at 3y, end at 9. Here is a dx dy double integral where we're describing this triangle. Okay? I'll try to trade this for outer. Every one of these double integral problems is a 2-for-1 deal. Always buy one, get one. So we've done a dx dy. Now we want to do a dy dx. So in this case, our y integral can use functions of upcoming variables. Y can use functions of x, but the x as the outer integral only gets constants. Start with your outer integral. What's x between? 0 to 9. Regardless of whatever shape we have, x is between 0 and 9. Now for y, we got to pick a typical x value. So for a given x value, y starts at 0 and ends at the line. So if we pick a typical x value, the lowest y value is at 0, and the highest y value is at the line. So instead of going from the line to 9, we go from 0 to the line. So we start off at 0, and we go up to the line. Now, the line in turn as a function of x is 1/3 x. This is how we play the game. What's x between and what's y between? Our early integrals can use functions of upcoming variables. Our outer integral gets constants. Notice I said use functions of upcoming variables, as in plural, because if you're wondering if we can just extend this by another integral, then yeah, we'll just say what's x between, what's y between, and what's z between. So that first integral, the innermost integral, we'll be able to use functions of 2 variables. The middle integral will use functions of 1 variable. The outer integral will use functions of no variables, just constants. Any questions? So we just set up these integrals, and I previously set the integral up with just a function of x and y, a generic function of x and y. Let's see how this works if we actually have to integrate a function. I'm going to integrate a very simple function. I just want to integrate 1. So we start off with our inside integral, which is a dx integral. So the integral of 1 with respect to x is x, and we evaluate x from 3y to 9. This is just doing the x part. So this is all still in an integral dy. This is why it's okay to use functions of the upcoming variable, because the upcoming variable is going to have us integrate with respect to y. So it's okay if y shows up. If I still had an x running around, I'd have a problem because I've already dealt with all the x's. So I can't have no more x running around. But now I've gone from my double integral to a single integral. I just need to integrate 9 minus 3y from 0 to 3. So we find the antiderivative, 9y minus 3 halves y squared, and evaluate from 0 to 3. Now we've finished our integration. We just have to plug in 3 and 0. Both double integrals should give the same result. If the two double integrals do not give you the same result, one of them is wrong. This could mean that both of them is wrong. I'll remember when I say one of them is wrong, it could be that both of them are wrong. Because if both of them are wrong, then one of them is wrong. That's just how OR works. Let's integrate the same function, but in the other order. dy dx. In the dy dx integral, y went from 0 to 1/3 x. And x went from 0 to 9. So now we're integrating with respect to y first and evaluating from 0 to 1/3 x. This is still sitting inside an integral that we haven't dealt with, so we have to keep writing it. Now I have to keep color matching because I can't stop. I don't know why. So in this case, we integrate the 1/3 x and we get 1/6 x squared. Evaluated from 0 to 9. So here you get 81/6, otherwise known as 27/2. The fact that both double integrals return the same amount does not guarantee that we're correct, but it's pretty strong evidence that we're correct. The other thing that gives pretty strong evidence that we were correct is that 27/2 is the area of the triangle. And if you integrate the function 1, that should give you the size of the region. This you already knew. If you integrate the function 1 from A to B, you get the length of the interval from A to B. So if you integrate the function 1 over a region, you get the area of the region. So the integral from A to B of the function of 1 dx will be b minus a. That is the length of the interval from A to B. It's length times width, but length is always 1, so the number that comes out is just the width. Well, I wanted to say also. Let's just say so. That's fine. It's fine. The integral over r of the function 1 dA will tell you the area of the region R. Because if we take height times area and the height is 1, then that number, that volume with a height of 1 is going to be the same value as the area. How's everybody okay? No, it would if your two double integrals do not agree on the value, then something is wrong. Because you're trying to describe the same thing. The integral over r of the function dA should give you the volume under the surface and above the region. So if the two double integrals disagree on the value, then someone is wrong. This is math. There is no agreed. Someone is wrong. Good question. I suppose if your function is discontinuous at some place, but then we're not doing this anyway. If the function is, say, discontinuous, like you have a vertical asymptote like on 9, then then none of this is really even a question in the first place. We need to talk about this. We need a continuous function. It's one will break sooner than the other. In the one that I described, in this continuity, one will break sooner than the other. There are some situations where the dx dy integral will be preferred over the dy dx integral because you can't do one of them if you're actually trying to calculate it. Like the first step is to integrate some function dx, and it doesn't have an antiderivative. So that's just a full stop. You have to go do something else. Switch the order, and then you can move on. But that's a niche problem. When I ask that problem, and I will, when that problem shows up on the homework, it's specifically so that you recognize that there's a function that you can't integrate. It's like an e to the x squared or something. But if you switch the order of integration, then you can integrate with respect to y and then move on with the problem. But that's a niche problem. It's designed to do that thing. Question? Yes. So we're looking at this picture here, which in my usual fashion, I drew way too small. But what we're going to do is, so for, let's take this line here. For a given y value, so pick a y value, that's when we were setting up this double integral. And we did our outer integral first because it has to have constants. We're going to do something with all the y values from 0 to 3. So we're going to pick one of those y values, and then go up to the region. And the region starts here at the line, and that's the first x value that we want to write down. And the last x value that we want to write down is 9. So that's why we start off at the line and end at 9. So that's what I meant by that. Now, if in the other direction, for this one, we're going to do something for all the x values between 0 and 9. So if we pick a typical x value, the region starts down here at 0 and ends when we get up to the line. I had to describe the line in 2 different ways because in the first case, I needed the line where x is a function of y. In the second case, I need to describe the line where y is a function of x. The setup is going to look different, but if we integrate the function 1, we should get the same. If I change my function to some different value, say that the density of this triangle is variable. So instead of saying 1, if the density increases with y, then this one has more y than the previous one, so it's going to be heavier. Well, we got to describe this upper triangle. And once again, we want to do a dx dy and a dy dx. Left to right, up to down. Down to up, actually. Down to up. In our usual fashion, we're going to start with the outer integral first. The outer integral only gets to use constants. So in our dx dy integral, I start with what's y between. Y goes from 0 to 3. Now for all these y values, if I pick a typical y value, x starts off at 0 and ends at the line. So here, x is going to go from 0 to 3y. Because that's how we describe the line as a function of y. In the other direction, with the dy dx integral, we'll assign the outer integral first because it has to be constants. The x's all go from 0 to 9. Now, for a typical x value, we see what's y between. Y starts at the line and ends at 3. So I'm going to write down start at the line, 1/3 x, and end when you get to 3. Now, in this case, since this is just the upper half of the rectangle, if we integrate both of these with the function 1, we should just get 27/2. So let's do that real quick. Let's see. 27/2, and then do the other one. Also 27/2. I'm really fast at calculating double integral when I know what the answer is. Now, once again, we're getting the same value because both of these double integrals, okay, we will get the same value if we integrate the function 1. We'll still get the 27/2 because of geometry. But these two will be equal because they're describing the same volume, the same area. The only reason that these two were equal to the previous ones is because of the geometry of the situation if we integrate the function 1. If we change this function to an x squared, then this is going to give us different values than our previous region. X squared will be different over this region in both these cases. We always go from left to right or from bottom to top. So we could go from like -2 up to 7. That's a great question. Was that? Yeah, because I always do the same thing. I am super predictable. So we could cut this part of the region and get, like you said, get away from the corner. So like this part region up here. Yes. We could integrate over this region. So x goes from 0 to 9 still, because I'm just using the same rectangle. That's called recycling. In this case, we have a different line. Our line, as in terms of y, our line, our y line is y is equal to 3 minus the slope is -1/3, so -1/3 x. So we could turn this around for our x line. So I'd have I have to write the stuff in between. So multiply by 3. I have a really hard time going like thinking lines this direction. So for our x integral, or for our dx dy integral, we have the same restriction on y. Y goes from 0 to 3. And for a typical y value, we start at the line and end at 9. So we'll start at the line and end at 9. For the dy dx integral, the x's are still between 0 and 9, but the y starts at the line and ends at 3. Starts at the line and ends at 3. I guess short answer to your question, yeah. We can break up the rectangle. But we always want to see what it's in between, what the x is between, and what's the y between. Now, if we have some funky shape, we're still going to want to know what x is between and what y is between. In this case, we just wouldn't have constants for our funky eyeball shape. All right, that's going to do it for today. I will see you all. That's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend, and thanks for playing. If you have questions, I'll see you in office hours tomorrow, either in person or on Zoom.